I hope everybody is fine by the grace of Almighty. And in this video, I'll be discussing the matter waves. And it was Louis Debroglie that that he predicted uh, the the presence of the existence of matter waves. Now, what led de Broglie basically to suggest that matter has a wave associated with it, and why it led to him that that the wave nature is basically the characteristic property of the microscopic particles. Now, in accordance with the theory of relativity, we have Einstein's equation of mass-energy relationship E equals mc square. So, uh, so, so, in accordance with the theory of relativity, we have we have E equals mc square as an equivalence between energy and mass. And similarly, in accordance with quantum theory, so here it is special relativity. Okay, so then in accordance with the quantum theory of radiation that we have been discussing, which was proposed by Max Planck, a radiation of frequency nu. It consists of a quanta or a photon having an energy equal to h nu, right? And these two basic ideas and some other theoretical considerations led Louis de Broglie to prove in 1924. It was in 1924 that matter also has dual nature. Matter has dual nature. So, what dual nature means here, we all understand. Dual means the matter can have both properties. It behaves like a wave under certain circumstances, and it can behave like a particle under certain circumstances. Now, according to him, according to de Broglie, protons, which ordinarily behave like particles under certain conditions, behave like trains of waves. And the wavelength of these waves depends upon the momentum. It depends on the momentum, which in turn depends upon the mass and the velocity of the particles. Now, according to the hypothesis, the hypothesis that de Broglie came up with is that according to the quantum theory of radiation, frequency consists of quanta that I'm talking about. We also call them as photons, and the energy of these photons is given by h nu, and where h is Planck's constant, right? And the value of this Planck's constant is 6.62 into 10 to the power of minus 34 joule second. So the equivalence of mass of the photon, if we go here, mass of the photon is what? It is it's E by c square. And for this E, if we replace this E by the Planck's energy, then this mass will come out to be h nu by c square. Right? So, since what we are predicting here is that since the speed of the photon in free space is c, that's the velocity of the light, the equivalent momentum of the proton, which I am considering here, for proton, if I say the momentum of proton is mc, that must be equal to E by c square, right? And this can come out to be for E we have h nu by c square times c. This c and c will cancel. So the momentum of this proton, which I considered in this case, will be so momentum will be h nu by c, right? And this nu by c is nothing but we have nu is c by lambda. So for nu by c, I have 1 by lambda, so this is h by lambda. So this equation that we have here is called as Debroglie equation, and this equation predicts the dual nature of matter waves. And what matter waves are considered here is the microscopic particles like electrons, protons, neutrons, atoms, molecules. So what de Broglie suggested is he suggested that the moving particle is associated with a wave, and the frequency of the wave is taken to be the frequency of that wave is taken to be E by h using Max Planck's equation. And the wavelength of the wave, what comes out to be lambda is h by p. Now p is the momentum of a material particle, and v. So this v is the velocity of the wave, or velocity of the particle that we are talking about under these considerations. And this equation, that lambda is equal to h by mv, this is known as de Broglie's wave equation. And we can see here that this equation is solely connected to this Planck's constant, which is 6.62 into 10 to the power minus 34 joule second. Right now, this is my de Broglie wave equation, where this lambda is called as de Broglie wavelength, and the associated wave, the associated term that's connected with this equation is matter, and matter has associated with it a guide, a pilot, or a de Broglie wave. So if I write down the phase, if I write down the phase velocity here, now if the velocity Vp equals nu lambda, right? So if I go with this new, which was already there, for new, I can use mc square by h times, for h lambda, it is h by mv. I'm going to get the phase velocity as v square, c square by v. So the phase velocity is c square by v. And this thing will be discussed in detail in the coming lectures. But here I'm trying to concentrate the terms that are linked with de Broglie equation. And so this thing that we have here is the phase velocity. Now, like other waves, the de Broglie wave can also be presented by a function, by a wave function, basically, by a wave function. And and this wave function, as we take it as psi, can be the function of some distance and time, and a function of positive r and time here. Now, it's known as the wave function, as I said. This is called as the wave function, and what it does, it's representing matter wave guiding the particle. So what it does, it is representing matter wave guiding the particle. And the wave function, this wave function can be, it can be positive, it can be negative, and it can be a complex quantity. It can be a complex quantity. And it has amplitude, and it has modulus, and phase like other complex functions that we know. And it has associated with it the wave vector, which I would like to define here. Wave vector, it's symbolized as k, as k. This k is also called as propagation vector. This k is also used in reciprocal space in solid state physics. Now, this k is basically, this is k is 2 pi by lambda. The reciprocal of wavelength gives us the measure of it gives us the measure of k, and I can proceed from here. Say this k is 2 pi by h by p using de Broglie equation, and this k is p times 2 pi by h bar. Now, we use a notation here, sorry, this is h only, that h bar is h by 2 pi. Okay, so here this k can be written as p by h bar, where this h bar is h by 2 pi. Now, if we move on from here in the same direction, now suppose if I have the moving particles, and the moving particles have kinetic energies. Moving particles have kinetic energy, say E. Okay, so I would like to translate the de Broglie equation in terms of the kinetic energy of the particle. Now, how can I do that? Is this kinetic energy is 1/2 of mv squared. I can write it like mv whole squared by 2m. So here I will have E as kinetic energy. So mv is momentum square by 2m. So this implies this p square is 2me. So this p is under root of 2me. Now I can think of writing down this de Broglie equation in terms of wavelength, in terms of kinetic energy. So I have what I have is lambda is h by p, but for p I can use here under root of twice me. So this lambda will be h by under root of twice me. Why this E refers to the energy of the particle, right? Now, if I go in the domain of kinetic theory of gases, where we calculate the averages, kinetic theory of gases, and what we calculate here is the average kinetic energy, average kinetic energy, and that average kinetic energy is uh, is 3 by 2 kT, and this k is Boltzmann constant. This k is Boltzmann constant, and its value is 1.38 into 10 to the power of minus 23 joule per Kelvin. And this T is the absolute temperature of the gas. So I can think of developing this. I can think of calculating the wavelength in terms of the average kinetic energy. So what am I going to get here is that that what I have for lambda is h by under root of 2me. Now, if we replace this e by the average kinetic energy, so it will come out to be h by 2m times 3 by 2 kT. This 2 and 2 is going out, so this is h by under root of 3m kT. So here we have the dependence of wavelength with the absolute temperature, and we can be in a state of calculating the wavelength using this equation, where we have where we know the absolute temperature of the system that we are dealing with. And to move on from here, we can also think of calculating this wavelength in terms of the electrostatic potential. Now we have electrostatic potential. Now, if I talk about this energy as kinetic energy, and this kinetic energy is equal to the potential difference, right? Choosing an electron having charge E and potential difference V. So the kinetic energy is equal to the potential energy of the electron. So from here, if I directly take it as E, so I can write down lambda. Lambda is h by under root of 2m eV. So this will give me the measure of the wavelength of an electron. If I'm accelerating an electron in a vacuum tube, it has the kinetic energy, and this electron can move under this potential difference of eV. Then I can measure the wavelength of that electron using this equation. Now, if we take the values from this equation as for the value of h as Planck's constant, that's 6.662 10 to the power of minus 34 joule second. Then we have the mass of the electron that is 9.1 into 10 to the power of minus 31 kilograms. The charge of electron is 1.6 into 10 to the power of minus 19 coulombs. And keep the potential difference as its. On evaluating these constants, what we get is that lambda comes out to be 12.26 into 10 to the power of minus 10 meters by under root of V. And as we understand that this 10 to the power of minus 10 meters is 1 angstrom, so this is 12.26 angstrom by under root of V. So all we need to know is how much potential difference we are applying across an electron. We can measure its approximate wavelength. So if I choose in this equation, say I'll choose different values of velocity, the different values of potential, then in that case, say if I take a case with V equal to 100 volts, so using that for lambda will give me 12.26 by under root of 10 squared angstroms. So what am I going to get here is the square and root will cancel. I'm going to get 1.226 angstrom. Now if I use 1000 volts, so lambda will come out to be 12.26 by it will be under root of 1000, and this can be simplified as this is 2.26 angstrom divided by 10 root 10, and when we will evaluate it, it will nearly come 0.338 angstrom. And can choose V equal to say 12,000 volts, right? So in that case, what we are going to get is 12.26 by under root of 12,000 angstrom, and this will come out to be 0.1119 angstrom. So this is how we can measure the wavelength of the charged particle that's accelerated across some potential using the de Broglie wave equation.